Check the time. Okay, hi, my name's Jim. I gave a talk 3 years ago at PyData meetup in London, and it was actually the first recorded talk on an open source feature store. And today will be the first of a new next generation of feature store. I'll get to it at the end. That's the promise. So this talk is about feature stores, but it's within the context of a problem. So a year ago, I moved apartment, and I found this CD up in the corner, and it was a project that I worked on in 2004 with Kieran Lee, who subsequently co-founded Intercom. I think he's 63 on Ireland's rich list. But the problem was basically, I used to love surfing, and he did too, and we wanted to go down to the west coast of Ireland at the weekend, and would there be surf, would there not be surf? So what we did was we built a system. Of course, it was machine learning, and we even published on it in ICML. And it was basically taking open ocean swell predictions. So the Americans have these buoys or buoys out in the Atlantic, and somebody on the west coast of Ireland, in a shop in Lahinch, he basically measures the height of the waves every day, and he publishes them. So it's a very simple curve fitting problem. And just a little bit of background, so you learn a little bit about surfing, one of my passions. Waves, as you know, have a direction. They have a period or a wavelength, and they also have a height. So you can see on this image on the right, we can see that the swell is coming in from the north, and you can see it hits this point. And at that point, you can see the lines compress. So the wave actually increases in height. The period stays the same, but the wavelength decreases. And you can see at the beach that the waves are much smaller than they are at the point. So the problem of predicting the height of a wave at a beach has a lot of parameters around it, but these are the main ones that you need to know for the predictions out in the Atlantic. So in the Atlantic, it looks like this. If you look on the bottom left, there's an image, and you can see there's a buoy out there, and that's a buoy run by NOAA. And we can see that it's producing this tabular data. You can get it on the internet. And it has actually information on the height of the swell, the period, and the direction. And you can see there's actually multiple swells here, because in the Atlantic, you can have different storms sending in swells. So you need to pick the right swell, because we'll see that some of the swells may go into the beach and some don't. So a bit of feature engineering will be needed. Somebody on the beach gives us these reports, which we can scrape from the website, which is great. And we do need to do a little bit more feature engineering, because we get these predictions out in the Atlantic at a certain time, but it takes a certain amount of time for that swell to reach the beach in Ireland. So we need to do some feature engineering there. It's not too hard, because you can calculate the swell velocity by multiplying the swell period by 1.5, and you also know the direction of the swell. So you know roughly when this swell is going to hit land. A lot of surfing. You didn't think you'd come here for surfing. And we also need to know the angle of the swell coming in. So when we have multiple swells, we're going to pick the best swell based on whether it fits inside the swell window at this particular beach in Ireland. Now, here's what we built. This is where it's kind of we're into the meat of the talk. So we built a system, and it was about 8,000 lines of code, primarily Java, PHP, a lot of SQL, and it was a k-nearest neighbors model. There's actually a few of them, and we'd kind of average over them. And the question I had when I saw the CD last year, I said, well, geez, I wonder if I re-implemented this thing, right? What would it look like? And the reason why our website is no longer online, if you go to CJ Surf, we had that on a website, was it cost, I think, like $100 a year to host it, and we had no cash. Like, he may be one of Ireland's richest people now, but we had no cash at the time, so we just let it fall. So what if you could write this system on free managed services, including a feature store, in 2022. So that's what I'm going to talk about here. Can we redo this thing in Python, and can we run it for free without having to pay anything? And the answer is yes, of course, but we'll see it in a second. So the system that we started out with at that time in 2004 was a LAMP stack, right? So we have a Java program scraping from these websites. It's writing data to my SQL server. It's using KNN to make predictions. We trained a model, and it writes the predictions to our database. And then we have a PHP web app, which looks up the pre-computed predictions, and you get to see your surf height at the beach. So what would that LAMP stack look like if you were to rebuild it as a serverless web application? So what you would need is, on the left, you'll need some sort of serverless orchestrator. We need to run the feature pipelines to pull the data from the observations, the swell predictions. We'll need to make predictions. We need to have a batch program which runs once a day, because we get new data once a day. In fact, we'll see we get data every 6 hours from the buoys. The data from the beach only comes once every day. You need to train models, but you can do that offline. And then we'll need somewhere to store this data. So we're going to have these features related to the surf report observations and the swell predictions. And we'll need to have a model. We'll need to store that somewhere. And then we'll need to have some sort of front end that we can provide to users. So this is what I'm going to show in the talk. We basically have to use some sort of orchestration tool, which you can use GitHub Actions. There's a bunch of other ones out there. I'm going to use Jupyter Notebook for model training because it's on my laptop. Hopsworks is the platform that we build. It's an open source platform. It's also now a serverless platform, we'll see at the end. And it has a model registry in it, and it has a feature store. So it's actually best known as a feature store because it was the first open source feature store out there. And what we'll do is we'll look at how we can write the features with feature pipelines to Hopsworks. We can train models in your laptop or in Colab. And you can then write predictions to the feature store as well, and they can be consumed by a Streamlift app. So those of you who don't know Streamlift, you can write a UI in Python very easily. It's very few lines of code. The whole thing went from 8,000 lines of code. It's open source. I'll give you a link later. It's less than 1,000 lines. I'm not sure exactly how many, because it's notebooks, and I don't know how to do a WC-L in a notebook yet. So there is another way you could do it on our platform, but I'm not going to talk about it today, just in case you're curious. You could also deploy the model on our platform, because we're also doing serverless model hosting, so deployed models. It's Kserve under the hood. And your Streamlit application could make predictions as requests come in, using pre-computed features in the feature store. But we're not going to do that today, but maybe if you're interested, it'd be a really interesting alternative architecture. So what I thought I'd do, the reason why I thought this was an interesting project to begin with was the feature store and feature engineering, you have a lot of challenges. And we solved a lot of these challenges when we built CJ Surf. And one of them that you have is point-in-time joins. And I'll show how it's easier in the feature store. So we had two tables. We had the surf reports in the top left-hand corner. So these are coming from Lahinch. Tom was putting these out daily, and we were scraping them and building up the tables. And then we have these swells coming in from the NOAA boys, and they're updated every 6 hours. So you can see they have different update cadences. The one on the left is updated daily, and the one on the right is updated every 6 hours. So when you want to create training data to train a model, you need to account for that difference. So what you need to do is what we call a point-in-time correct join. We don't want any data leakage. What we want to have, if we look at the training data at the bottom, for every row we're going to take the observation in the table in the top left, so the surf report observation, and we're going to pick out the height, direction, and period at the hits at time. So the hits at time was the time we predicted this swell would arrive at the beach. But we don't want future data in there, right? So we want the most recent hits at observation on the right. We don't want one that's too early, because then it won't be good. We want one that's too late, because then we'll have data leakage. So this is how we did it this is just some code I pulled out of the source code I found. You know, it's pretty ugly SQL. Like, it's not super easy to debug, not super easy to embed in your programs. It's an SQL bomb. That's actually a wave in Ireland, in Sligo, Mullaghmore. We have a summer house down there. It's lovely. So this is how you would do that. So obviously, people aren't interested in looking at SQL and going through it. But this is how you would write this in our platform, Hopsworks. You can see we have a DSL. So it's a Python-based DSL. And Lahinch there is what we call a feature group. It's a representation of this table. So the term feature group is used in feature store to represent tables of features. And we have a second feature group called swells. So what we're doing is we're selecting the feature called wave height from the Lahinch table. And we're selecting from the swells table the height, the period, and direction. And we get back what we call a query object. And you can just inspect the data. You can get a data frame from it, have a look at it. What we typically do is we create a materialized view of that query. We call that a feature view. So it's a view over the tables that are there. Because in a feature store, you're going to have many features in many different tables. And you'd like to reuse those features across different models. You would say, I'd like that feature, that feature, that feature. Give me some training data. And this is the API for doing it. So, you know, if you read the intro to the talk, it said, well, you know, how do people do this in feature stores right now? The world has kind of gone into two. We have the Python community here, and we have the SQL community here. There are many people in the Snowflake new SQL, new data warehouse kind of space who think that all of this should be done in SQL, and it should be run directly on your backend. Actually, we agree, because you're not going to be able to do this point-in-time join if you're downloading data frames in pandas that are, you know, terabytes in size. You're not going to be able to do this. You want to have technology that enables you to do this irrespective of the amount of data at the back end. So you can write it purely in SQL in, Snowflake or Redshift or BigQuery, but we saw what you have to do. You have to write this horrible code. So what we have here is a nice DSL. It transpiles into SQL, and then we execute it on the back end in our platform. So from your perspective as a developer, you're writing Python native code, but it will scale out if needs to at the back end. And then this set of features that we get together, we call that a feature view. We'll go into that in a little bit. So that was problem number one. The second problem that we had is that we saw actually earlier, Sarah had a talk where she talked about just this problem with standard scalars and scikit-learn, that maybe your inference pipeline is different to your training pipeline. So if you have, in our case, we have 3 features, height, period, and distance of our swells that we're going to use to predict the height of the wave at the beach. What if we normalize these? Will it improve the accuracy of our model? This is actually a classification problem, but I just showed the RMSE because it's more intuitive, I guess. But you can see that normalizing them makes a little bit of difference. So wouldn't it be nice to normalize these features for training and also in our inference pipeline? And you can do it, and we did it before. But what you have to do is you have to ensure that you're using the same code, the same transformation functions with the same parameters. And Sarah showed how she exported the parameters to files and read them up again. But you can also just dump your scalar object and read it up again, as long as the version of scikit-learn in inference is the same as it is in training, which is of course a potential problem. So there's a lot of issues can arise in this. We call this training serving skew when there's a difference between it. So in our platform, how you handle training serving skew is you can write your own transformation function. We have obviously built-in transformation functions like scikit-learn's standard scalar. And what you do is, you can see here on the top left, what we have is in this case, I'm applying the standard scalar to 3 features. So I say, okay, these 3 features, I want to run them through standard scalar. And then all I need to do is call train test split, and I'll get back my training and test sets and labels, features and labels. And then in inference, I don't do anything. It's like, so what has happened here is that the feature store is storing the metadata about the transformation. So the standard scalar parameters that we saw in Sarah's talk, they're being stored in the feature store, and then they're being retrieved transparently from here. Because this feature view object that we have both in training and in inference, it knows about the data that you trained on and the parameters of the features, so the descriptive statistics that are used to compute to compute the transformation function here, the standard scalar. So a third problem that you have is, well, what happens when I'm downloading from Tom's website if he put in 100 instead of 10 foot for the height of the wave, which might be an outlier. We didn't obviously do any data validation back at the time, but what we've added to our platform is something called Great Expectations. Many of you may have heard of it. There was a tutorial yesterday. So what you would like to happen is that your data is validated before it's written to the feature store. And in this case, if you look in bold, you can see that I've added an expectation saying the wave height should be between 0 and 20, because you don't get higher than 20-foot waves at Lahinch. The other place was Mullochmore, that's a lot higher. And what you do then is when you define your feature group, the table of features, you just say, this is the expectation suite that we have defined in Great Expectations, and every time I insert a data frame, because when we write to the feature store, we write data frames, so pandas data frames or Spark data frames, it'll validate the data before it's written to our platform. There is one other feature store which does the opposite, which we think is a bit crazy, where they validate data reading from the feature store. So in general, I think it's better to have clean data in your feature store from the beginning rather than validate it when you're reading it. So you get these nice visual reports that we'll see in a little bit later. Okay, so what is a feature store? I've talked about some of the problems that it solves. I haven't defined what the thing is. This is our view of a feature store, because I think this, as if you're a developer, this makes it as easy as possible for you to think about the concepts. You're going to write these feature pipelines to create features, and they'll write these things called feature groups. Feature groups are the tables of features, and they're mutable. You write to them, you update them. The feature views, on the other hand, they read. That's where you want to read from the feature store. You create a feature view. And reading can have 2 different components. You can read from the feature views to create training data or to create batch scoring data. So it's going to be a high throughput API to get you CSV or TF record files or to get you pandas data frame. And then when you're in inference, you might want to read your pre-computed features. You're going to say, okay, give me these swell, direction, and height of the waves. And you want that to happen at very low latency. So this is where the feature store is slightly different to a data warehouse. We have a very low latency API for online serving, and then we have a high throughput, high bandwidth API for offline access. Now, internally, how that's implemented is that you have one database, so it's a dual database system. All feature stores out there now are dual database. There was one that was hybrid, but it's actually now since the company went bust. But you basically have a low latency database for the online API, for retrieving the feature vectors, and then you have some scalable database for the offline data. So in our platform, you can have your offline data in any external data warehouse, so you can mount them in. But the online data we store in our own database called RonDB. So we're actually ex-MySQL people, and Mikael Ronström's, it's a fork of a database called MySQL Cluster. And then offline, if you do write the features offline to our platform, we use Apache Hudi. And the reason why we use these technologies is that you want to have guarantees when you're writing the data that when it gets ingested, that you have consistency of the features between online and offline. So we achieve that by writing to Kafka, which gives us at least once semantics guarantees, and then through idempotency to the online feature store, and then the ACID properties of Hudi writes, we ensure that the data lands, the data is consistent between the online and offline stores. And you have to ensure that the schema matches across them. So I defined what a feature view is, but let me just walk you through the steps of creating a feature view. So we've got our two tables of features at the top, the surf reports from the beach, and then we've got the predictions from the ocean. So we're going to select the features from those different tables, and then we're going to apply transformation functions to some of those features. So a feature view, if you think of it as a type, a set of columns, it actually also has transformation functions associated with the data types. So a feature view is not just a set of data types or columns, it's also the transformation function. So it's an extended type, if you will. And then you also want to define the label, because we're doing supervised machine learning here, when you're creating your feature view. And then the feature view can be used, as we see in the middle, for get feature vectors, for retrieving individual feature vectors, for serving. And then when we want to create training data from it, we can say, well, do I want pandas data frames or files? Can I filter out, because maybe I don't want to have all the data. I want to filter out just the beach Lahinch and just the boy 68021. And then I want to maybe create random splits of my data, or maybe time-based splits. You can do that all in the API. So the feature view kind of looks like this. The data is being written to these feature groups, and the feature view allows you to create these immutable snapshots of training data and batch scoring data. So when you train your model, you'll say, I'll have the data from this starting point to this end point, and then you say, give me the data that arrived since then, and I'll score it. So in that case, that's what we're doing for predicting on our surf page. We'll say, okay, give me all the predictions that have come in from NOAA, and I'll compute or estimate the wave heights for the next period of time. And then finally, when the observations come in, you can create more training data and retrain your models. So the models themselves, we store them in our platform. So some of the things that you can do is, you create your training data with this feature view API, and then you're in Jupyter or in Colab, and you want to train a model. So in this case, I use KNN, and I'll go through the notebook in a minute for training the model. And then other things you might want to do with a feature view is very useful. You can say, okay, I'd like to create evaluations or data sets. So you might say, in this case, there's no personal information involved, but if I was working with customers and we had, let's say, 10 different groups of customers, I might say, well, I'd like to have, from my test set, I'd like to create 10 different slices of that test set, sliced along these different groupings of customers. And then I'd score my model against all 10 groupings to ensure that the model doesn't have bias. So that's a really useful property that you can do with your feature views in the feature store. And then finally, when you if you want to deploy a model as an endpoint, so you're going to make calls over the network, you can do that as well in the platform. So I'm going to go through the code, but let me show you the whole architecture. It's all available on GitHub. So what we have here, if we look at it, is on the left-hand side, we have our data. So we have the website that we're going to scrape data from, the Lahinch Surfshop website. We have CSV files. We have so I found on my CD, I found some CSV files. Unfortunately, it wasn't great data because it was missing tons of data, but I kind of put something together. So so I have a program there's a notebook in this GitHub URL called Surf Report Feature Pipeline. I think it's the Hinch report for feature pipeline. And you can run either to backfill data from the CSV file to create your first set of features, and then you can run it not backfilling, which means it goes to the website, downloads today's observation or surf report, and writes it to the feature group. So these things, the surf report feature pipeline and also the swell prediction feature pipeline, they're feature pipelines. They're taking data, they're computing features as pandas data frames, and they're writing them to these feature groups. Now, once you have your feature groups in place, we create one feature view, that's all we need here, which will contain the height of the wave at the beach, and then the 3 parameters, the features we need to make the prediction on the swell. So the height of the swell, the period of the swell, and the direction of the swell. So with this feature view, we can create training data, and there's a notebook for that called Model Training Pipeline. And then there's another program called Batch Predictions Pipeline, and that is going to run, you should run that every day, right? It's going to make new predictions, you'll update the predictions. In fact, you can run it every 6 hours because NOAA update their swell predictions every 6 hours. So it would be probably better to run it every 6 hours. So what that program does is it just writes to the output to a feature group, because a feature group is just a table. And then we have a Streamlit application that shows you the wave height predictions. So I'm going to walk through these different steps. Let's look at, I did promise you we would do this serverless. It's not about GitHub Actions, so I'm not going to go through the GitHub Actions. But you can run all of these notebooks. You can use NB-convert to convert them to Python files and run them, and you can schedule them using GitHub Actions if you want. There are plenty of other free orchestrators out there. So that's one way of doing it. And then the data and the models, so the 2 feature groups, the feature view, the output predictions, that's another feature group, and then the model itself will all be stored in Hopsworks in our platform. And then finally, we have Streamlit to do the UI, and it kind of looks like this. This is just generated this morning. It's not particularly beautiful, but you can see that it's predicting the wave heights somewhere between 1 and 3 feet for the next week or so. So let's have a look at some of the code for this. Are you with me? Okay. So this is the platform here. You can see the URL in the top corner. Hopefully you can see that. I can zoom in a little bit. It's called Hopsworks.ai, and if you go to apps.hopsworks.ai, you can try and reproduce this now. But what we can see is, I'll start at the programs. We can see that there are the feature groups here. So we have feature groups. It's using my phone because the Wi-Fi sucks here, as you all, I'm sure, know. But let's have a quick look at the Lahinch data, because these are the features, the surf reports. So there's not that many features. We've got like the beach ID, because maybe I want to add this to other beaches. And that's our primary key. The observation time is the event key on this particular, so that's what we use for the point-in-time joins. It's the time at which the report is made. And then we have the height of the wave. In fact, there's 3 different parameters given by the surf report. They often give a max height, a min height. So you could extend this example to also predict max and min height as a label. But what we can see here, like if you have a feature store, you say, okay, well, I can see the provenance where these features are used for training. I can see when we had some expectations. In this case, we expected the wave between 0 and 20 feet, and we can see the result of them here. So if there were errors in the pipeline, you can see them here. You could also set up an alert here to get a ping in Slack to say, hey, there's a problem with the expectation or a problem with the job. So it's all this kind of useful tooling for getting this thing running. One thing that I find is very useful for debugging is just getting a quick preview of your data. So one thing I didn't mention, I mentioned there is an offline store and an online store. I didn't go into the details about those, but I'll mention it here. The offline store stores the latest value of features only. Right? It's typically used for because you're only going to use it to retrieve the latest values of features to make predictions. So in this case, you can see there's only one observation here, which is, this is from today, I believe. Yeah, no, this is actually an older one. This is a preview. It's not showing. It's just picking a random observation. So you can see that was the data we collected in 2004, and the height of the wave at that day was 3 feet. By the way, if you're curious, waves are measured in feet, and they're measured from behind. So a 3-foot wave is actually this high. It's called Hawaii, the Hawaii measurement. So that's the online measurement. So the offline store doesn't store the latest values of features. It stores the historical value of features. We're going to use that to create training data. And it's going to have all the values of features over time because they get updated over and over and over again in time. So you know, your offline store could have huge amount of data going back to a very, very long time. And we can see here it's taking a few seconds to load. So this is actually, you know, this data is stored on Hoodie, and it takes a few seconds to load. And you can see as well that we'll have a look in a second that when you write your pandas data frame to the feature store, this seems to be hanging. And I don't have to blame my internet or blame somebody else, but we'll see if it's the internet here. No. So this one moved on. So let's look at the statistics. So when you write this table of this pandas data frame, it computes statistics. I turned on computing statistics. You can turn it off if you want, but it's very useful for EDA. So you want to basically have a quick look at your data, and we can see here for the height of the waves that, you know, there's a lot of, if we look at the size of them here, you know, there's a lot of low waves that are quite small, and then there's a few of them that are very high. And you can see this, here's our wave height again here. So, you know, we also I computed a correlation matrix here. I don't know if that was of any use. But you can also see what's happened, right? So you can look at the activity on this particular feature group over a period of time. So we can see here that you know, I did a backfill here, and then I ran and downloaded from the internet, and off we went. So there's also feature views here. This is the feature view that I created, and we can see, like for this particular feature view, we have hundreds of features actually. So you can see here that not just the wave height and direction, but all of the, for every hour, I think it's for 120 hours, I have the swell height, the direction, and the estimated time it hits at. So you can have, you know, potentially models with hundreds of features. That's fine. And let's have a look at the code, because that's more interesting, I guess. Let's see how we're doing for time. So let's start at our feature pipelines. So how do we compute this? So firstly, you need to install a library. Hopsworks is all you need. In this case, I set backfill to false, but you know, that means it's going to go to the internet, download from the website the height of the waves, and it's going to have a data frame. So we're going to have a data frame. So either when we're backfilling or downloading the internet, we'll have this data frame df with our data. We define our expectation suite here. We log into the platform. So if you're just running this interactively, it'll redirect you to the website, give you an API key, which you paste in here. But you can set an environment variable as well, so it'll just go straight through. And then to write to the feature store, you can see it's pretty straightforward code here. We have this thing called FS object, the feature store object, and we just get a reference to that, and we call the get or create feature group. The name of the feature group, description, whether it's going to be online or not, a primary key, the expectation suite, am I going to compute statistics, and then the column that has the event time. And then I just insert that data. And it gives you a link to an ingestion job. So if you're using the serverless platform, it'll show you these were the jobs that ran to ingest the data and the results of them. You can get your logs there. And so that was the first pipeline, which is writing to the observations at the beach. The one from NOAA, which is our swell heights, we're doing something similar. We're going to the internet scraping data. We can backfill. There's more feature engineering in here because we have to select the correct swell. We can have multiple competing swells. So we take the one that's highest but within the swell window. And then we basically come down here. We have a data frame ready to go, and we just write it again. So it's very similar to what we saw before. You can see, you notice I don't have expectations set up here on this website because NOAA are pretty good. I didn't think it was needed. And then I want to train a model. So I need to have my feature view. So in this case, what I'm going to do is, again, we'll log into the platform. I've got some transformation functions that I define here. I need to do it over all the hours because we can have, in this case, I may have, you know, hundreds of features because I need 4 features or 3 features for every hour, and I want to predict the next 120 hours. So here I'm joining the features together. This is our DSL that I mentioned. You can see we've got the lakehouses feature group, the swells feature group. I'm basically selecting the wave height from the observations, and then I'm selecting all of the features from the swells feature group except the beach ID. And you can see that the SQL that you would have to write, here you go. Would you like to write that? Like, I wouldn't, like, seriously. But I didn't have to worry about it here. And then it's just, you know, you can see that my data was a bit dirty. I didn't have when we stored the data before, I didn't store the predictions for the next hour and so on, so a lot of NANs in the data. I just had the observations at the actual time. So I need to collect better data in the future. So with that query object, I can create my feature view here, and we say that the label is the wave height. There isn't that much data here, so typically I would just get back a pandas, 4 pandas data frames, the features, the labels for training and testing. If you want to store it on disk, you can call this. You can see here we can store the CSV files. You can also coalesce them into a single file. This is going to run a Spark job in the background, so it'll create lots of small files if you don't. But if you coalesce it and you don't have enough memory in the driver, it won't work. So you need there's a little bit of knowledge needed there. But if you write them to the platform, you can also just retrieve them, which is a bit faster. You can say, okay, just download the features and labels for the train and test sets. So in this case, actually, I got back a lot of labels, so I just selected the ones I needed for training. And then I'm using scikit-learn. I'm also encoding the label here. And then I'm using k-nearest neighbors to train the model. And now I just basically compute the metrics on the model. I did the RMSE just for fun, but it is a classification problem. So this is how it fitted, right? It wasn't like super brilliant. We had much better in 2004, but I didn't have correct data. So I'm going to collect data in the next while, and this will get better. But it's good enough. If you're surfing, it gives you a general idea if there'll be waves or not. So once I've got my model trained, this is where we have the data frame, which contains information about the features that we use to train the model. So that is actually used to create the schema of the model. Because you remember, your model has a schema, an input schema as well, and an output schema. So when we store our model in the model registry, yes, we serialize it. We dump it as a pickled Python object. But what we also do, which is very interesting here, is we can also store, you can see it says here, input example equals input example. So this input example is just a sample from the input training data. So if we store that along with the model, it means then when you're trying out your model and testing it, there's an input example ready. You can just press click and it's great. It's really nice for debugging your models. So then you save your model to the model registry. You can deploy it for serving, and you're good to go. So the last thing then, once you have your model up and running, let's have a quick look at that, by the way, because we didn't look at that. So the models here, you can see here I've got a model registry. There's only one called CJ Surf Model. I played around with the different versions of it. Everything is versioned here, by the way, including feature groups and feature views, and that versioning is the schema, because that's what you need to version above all else. That when you change the schema, make breaking changes, downstream clients should be aware of that. So this particular model, you can see we stored the model metrics. So when I published the model to model registry, I had a dict with the metrics, and that you can see them here. We can see that's being used in one deployment, and then we can see the input-output schema, and you can have tags and so on for governance. And then the model that's actually running, you can see it here, it's running. Now let's go and look at the last thing that we have, which is the prediction pipeline. So the prediction pipeline is the program that's going to run every 6 hours or every day to generate our new user interface. So what it's going to do is it's going to download our model, which you can see here. So it's going to connect to the model registry, download it, unpickle it, and then it's going to, and this is just testing the feature vector, but what it's basically doing is it's going to download all of the feature vectors for the from the online that we get when we say, give me the latest values of the features. So the latest values of the features will be 120 hours worth of input swell height. So NOAA tells us at hour number 1, we'll have this swell height period and direction, and hour number 2, it'll be this, and so on. So we're going to get a different set of features for each of those hours. So we're going to make predictions for all of those. So it's basically building up a data frame with those. And then we write the, then we have the prediction is happening, what do we say? Dun, dun, dun. Yeah, so then we actually make our prediction here. So we're making our prediction here, and we're writing out the prediction. It's just another column in our output data frame, and we write it out to the platform here. So then finally, the Streamlit app that looks here, that looks like this, it gives it the output. Its code looks like the following. It's pretty straightforward. It all fits on one page. We can see here that we give a title to the web page and a subheader, and we connect to the feature store. We read these pre-computed features from the online feature store of that feature group, and then we basically display them with a line chart. So it's just doing a couple of other things related to converting the types of the columns. So that's basically it. That's our end-to-end serverless wave prediction. I would call it a prediction service, right? So just a little bit like context. What we want people to be able to do with this is build prediction services, right? So if you want to demo to your colleague or to someone else that hey, I'm training a model and I can show the model fits the data, that's not communicating to stakeholders the value of your model. What does is a prediction service, something that's going to maybe predict fraud or maybe going to predict a recommender system. You want to show an end-to-end demo. And to do that, you need to build what we call an ML flywheel. Right? An ML flywheel is what I kind of covered there, that we have to have some data coming in. We had our data dump of the web heights and the predictions. We store them in the feature store. We train the model. We serve the model. In this case, we were doing an analytical ML application. And then we need to have a way of collecting new data. So we need to ensure that new data comes in. So features should get logged. Outcomes should get logged. And that new data will feed in to create better models. And hopefully better models will mean you get more data, which means you'll get better models, which means you get more users, hopefully, and better services. So this is what we call the ML flywheel, and you need to get it going. And you can do that in serverless with our platform, Hopsworks. So I did promise you that I would say announce something new. So we're announcing here now the first ever serverless feature store and also model serving infrastructure, or Hopsworks. And you can register here. It's exclusive to PyData London. We're not announcing this yet. And it's something you can use. This is not something that's a demo that we're going to take off you next week. Free forever, in inverted commas. As you know the conditions associated with that. But you'll be given, and I can show you some of what does that mean. If we go back to the platform here, we can see here, if we just look at our home, there's some quotas. So you can have like a couple of gigabytes of data. You can run 5 parallel ingestion jobs or training creation jobs, 30 feature groups offline, 2 model servings or deployments in parallel. Basically, you can build these prediction flywheels and try them out. And the barrier to entry, which is often just, I don't want to pay for a Docker container being served on SageMaker, we removed that. So you'll be able to build prediction services, not just models. And I think you can do that end-to-end in Python. I think this is an important part of enabling people to build end-to-end prediction services in Python. So if you want the slides, you can maybe follow my Twitter. I'll post some variant of them maybe this evening. Go to hopsworks.ai and app.hopsworks.ai if you want to try this out. Talk to us. We have a booth outside. And this is a cool one. Beers are on us. We're giving out beers. We're sponsoring beers this evening. So we're around. Talk to us if you're interested, if you find this in any way potentially useful for you. Whether you're just hacking or whether you're doing bigger projects, we're interested. Thank you very much. Yes. Yeah.
Oh, sorry. Hi. Okay. So the question is about ingress and egress from the warehouses. Is that a limitation potentially?
Well, when you write to the feature store, you write data frames, either in Pandas or in Spark. And I showed a slide where we ingest them into Kafka, and then we manage the consistency of them between the online and offline stores. So that's something you shouldn't have to worry about. Right?
But I guess there is the egress from the
Well,
warehouse,
the
right?
feature view we saw was the main mechanism for egress, where you read either training data or batch scoring data as data frames or files, and then you read individual feature vectors when you're serving and you need features to pre-computed features for your models. So that's the egress in this case.
Okay. Okay. And sorry, and the other question was just about if there is already some feature engineering happening, say with DBT, as part of well, a BI team or something, then is that something that can be kind of plugged in to just consume it?
We can take an existing table from Snowflake or Redshift or Data Lake and just mount it as a table, a offline feature group in there. I think there's one more, maybe time for one more.
Just quickly,
I'll repeat it.
The statistics, great, you calculate, I'm assuming you're calculating, hi, thanks. Assuming you're calculating that across the entire of the offline store every time there's a new ingestion, have you thought about, or do you have any plans for data feature concept drift tools, detection tools?
Yeah, so the question is related to drift, right? So there's different types of drifts. You have feature shift, not drift, because that's as individual feature changing, and then you have drift, which is typically concept drift, when a model doesn't make predictions because the underlying prediction problem has changed. So what we do is we do right now is we capture all of the logs, the feature logs. And there's two different types of logs, in fact, for features. You have transformed values and untransformed values. So transformed are pretty useless. So you need to capture the untransformed values. And then you have, obviously, the predictions. So we push them all into Kafka. And right now, you have to write a program yourself to do that, because every prediction problem has different notions of what is anomalous for that particular problem. So, there are algorithms. We actually have an out-of-the-box kind of one, which will do, Kale divergence, but that's pretty standard, and Wasserstein at distance as well. But that's something that we're working on as well. Okay, thank you very much.